Hello class, welcome to Geometry Lesson 8.2, Trigonometric Ratios. So our essential question today, how do trigonometric ratios relate angle measures to side lengths of right triangles? Our learning goal is to use these trigonometric ratios to find lengths and angle measures of right triangles. So our vocabulary includes these three trigonometric ratios, the sine, cosine, and tangent, as well as the trigonometric ratios. So let's begin with the definition of trigonometric ratio. These are ratios, which when we mean by ratio, we mean like a fraction, right? So it's a fraction relating side lengths of a right triangle to its acute angles. These are also known as functions because they behave like regular functions, like in algebra. So below is a right triangle, triangle ABC. And we're going to label the sides of this triangle. So we have the hypotenuse, the longest side in the triangle. We have what we call an opposite side. And this is the side that is opposite of angle A. So if we're interested in angle A here, then it's directly across or opposite of angle A. And then the side on the bottom below the angle here, this blue line, is the adjacent side. It is the side that is adjacent or next to angle A. The leg that is adjacent, that is. So it turns out that the trig ratios are just ratios of these sides. So we have our opposite, we have our adjacent, and we have our hypotenuse. So the sine of angle A, the definition is the length of the leg that is opposite of the angle divided by the length of the hypotenuse. And then the cosine is the adjacent leg divided by the hypotenuse leg. And this is the cosine of angle A. And then the tangent of A is the length of the leg opposite of A and divided by the length of the adjacent to A. And so these are all color-coded so that you can look at the sides, orange and blue. So the acronym that we use to help us remember this is SOHCAHTOA. Now for this, you can kind of see that A is the adjacent side, H is the opposite, or O is the opposite, and H is the hypotenuse. And S, C, and T stands for sine, cosine, and tangent. So for example 1, find the values of sine, cosine, and tangent for these two angles. So if we want to do the angle H, so let's do angle H first. We want to, so if you remember the SOHCAHTOA, so we'll go ahead and write that out. We have SOHCAHTOA. So S is sine, and it stands for opposite over hypotenuse. So we have the sine of angle H, so we're going to do sine of H here, is equal to opposite over hypotenuse, and opposite of the angle that the side that is opposite of H is straight across from the angle there. So the opposite here is 12. Hypotenuse is 15. And then that's my sine. But of course we're going to want to reduce this, so we're going to divide top and bottom by 3. And so that leads us to the solution of 4/5. So we got sine, so let's do cosine of H. So that's going to be SOHCAHTOA. So we have AH. So we have A over H. And this H is not the same as this angle H, right? The H is the hypotenuse. So not to get confused with angle H. So cosine is adjacent over hypotenuse. So this has to be the adjacent side, the leg that is next to the angle. And it's always going to be shorter than the hypotenuse. So we got 9 over 15. Then we want to reduce it, divide by 3 top and bottom, and we get 3/5. Then we'll finish off with tangent, which is OA, O over A, which is opposite of H is that 12, and adjacent is 9. Then we'll divide by 3, and we get 4/3. All right, so now let's finish it up for angle F. Let's do this in another color. So we're going to do sine. Actually, we'll go ahead and do it over here. So we got sine of angle H, or angle F, is equal to opposite over hypotenuse. So the opposite of F, this is F now, the opposite of f is now this one. So this is now going to be my opposite because it's directly across from f. So it's going to be opposite over hypotenuse. Then we reduce it and we get 3/5. The cosine of f is adjacent over hypotenuse. Adjacent is now 12. So we got 12 over 15, which reduces to 4/5. And then finally, we got tangent of f. It's equal to opposite over adjacent. So opposite is 9, adjacent is 12. So we get 3/4. And you'll notice that the sine of h is actually equal to the cosine of f. And the cosine of h is equal to the sine of f. So it's always the case that so in this case, we said the sine, the sine of h is equal to the cosine of f. And the cosine of h is equal to the sine of f. And this is because cosine stands for complementary sine. So cosine is actually short for complementary sine. And remember that complementary angles add up to 90 degrees, right? So h and f are complementary angles. And so this means that the cosine, which complements the sine, they're going to be equal to each other if I do it for the other angle. So if I switch it from h to f, then it'll all of a sudden be equal. And notice that we can't do this on the right triangle for this right angle. We can only do it for these two acute angles. All right, so let's look at another example. Find the values of sine, cosine, and tangent for the following special right triangles. So we have here some 45, 45, 90 triangle, which we've seen right triangles in the last lesson. So let's calculate the sine, cosine, and tangent. Now, so let's do the sine, cosine of and tangent of 45 degrees. So we have sine of 45 degrees is equal to opposite over hypotenuse. Hypotenuse is square root of 2. And then remember that in order to simplify this, in order to rationalize the denominator, we need to multiply top and bottom by the square root of 2. If not, go see the lesson 8.1 where we went over this. And then we have to multiply the top, and then square root of 2 times square root of 2 is the square root of 4. And we know that the square root of 4 is 2. So this becomes square root of 2 over 2. And that takes care of the sine 45. So let's do cosine of 45. Which is going to be adjacent, so this is adjacent now, over hypotenuse. But we know adjacent and opposite are really the same thing in this triangle. They're both 1. So we get the same answer. We get the same result, that the cosine of 45 is equal to the sine of 45. And this makes sense because remember I told you that sine and cosine are complementary angles. 45 plus 45 sine and cosine are complementary functions, rather. 45 and 45 is 90, so they complement each other. So if the angles add up to 90, that means that they're equal to each other. So like the cosine of 30 would be equal to the sine of 60, for example. We'll see that in part B. So we have this setup, and now we want to find tan of 45 is opposite over hypotenuse, so it's going to be 1 over 1, which is just going to be 1. So this is always going to be the case for a 45, 45, 90 triangle, that the sine is going to be equal to square root of 2 over 2, the cosine is going to be square root of 2 over 2, and the tangent is going to be equal to 1, the tangent of 45, that is. They're always going to be these values, no matter what. All right, and then for part B, let's do the sine of 30 degrees. Let's do the 30 degrees first. So we got sine of 30 is equal to opposite over hypotenuse. So it's just going to be 1/2. And then cosine of 30 is adjacent over hypotenuse. And then tangent of 30 is opposite over adjacent. And then we got to simplify this, remember? So we got to multiply square root of 3 because we don't like the square roots to be on the bottom. And then you get square root of 3 over Square root of 3 times 3 is 9. And then square root of 9 is 3. All right, and then we're going to finish up with the 60 degrees. So we got sine of 60 degrees. This time we're interested in this angle. So we got opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite, square root of 3, over adjacent, which is 1. Which is the same thing as square root of 3. All right, so notice what we said before, that the sine of 60 here is equal to the cosine of 30, and the cosine of 60 is equal to the sine of 30. Like we said earlier, they're complementary functions. So if I find the complement of 60, which is 30, to add up to 90, then the complementary function of that is going to be the same answer, okay, the same ratio. All right, so like I mentioned earlier, these values for sine 45, cosine 45, tangent, sine 60, and so on, they're always going to be the same. And you can do this on the calculator. So on the calculator, you have the functions in the middle. So on a standard calculator, they have sine, cosine, and tangent written like this. But remember that when you calculate these values, the calculator must be in degree mode. Okay, so we'll show you how to do this on the calculator in the next lesson, or in the next slide here, the next example, which is example 3. So calculate the following values of the given trig functions to the nearest thousandth. So we're going to do sine of 35 degrees. So in order to show you this, we'll go ahead and plug it into the calculator here. So here is a calculator. Let me go ahead and slide this. Well, we can slide this over for a second. So we want to do the sine of 35 degrees. So we're going to hit, this is the TI-30XS, similar to the model that I showed you in the previous slide. So here are the functions, sine, cosine, tangent. So we're going to hit sine of 35. And make sure your calculator is in this degree mode. You see that this is in degrees here, DEG. And then enter. And we got this 0.5735. So we're going to round it to the nearest thousandth, 3 decimals. So 0.574. All right, showing the next one, cosine of 57. We can do it over here. So we got cosine of 57. 0.545. And finally, we got the tan of 82. Which is 7.115. All right, so now you know how to plug it into the calculator, and there's plenty of calculators have sine, cosine, and tangent. They're actually very common functions. All right, so now this next example, we want to find the angle given the trigonometric ratio. So we're going to have to, so we're going to show you how to calculate this. This time we want to do the opposite operation. So we'll show you how to do this in a second. Okay, so in order to calculate the angle for sine, cosine, and tangent, you're going to have to do what we call an inverse trigonometric function. Okay, so in order to calculate this, so normally in algebra you have when you're solving for x, you have to if you had, for example, x plus 5 equals 10, you would have to subtract 5 on both sides and do the opposite operation here, right, in order to solve for the variable. Similarly, if we had 5 times x equals 10, for instance, you'd have to do the opposite of multiplication and divide. So we always have to do that opposite operation. And then finally, we discussed, like we've done, where if you had x squared equals 10, the only way to get rid of that squared is by doing a square root. So you always need an opposite operation to cancel what you have to isolate x. This time my variable is this Greek letter theta. Okay, so don't get confused by that variable. It's just a Greek letter. We use that Greek letter commonly for angles. But you can use x, y, or z, it doesn't really matter. But theta is just very commonly used. So if we want to solve for theta, get the angle by itself, then we have to do the opposite of the sine. And the opposite of the sine is the inverse sine function. And it looks like that. So it's sine with a little -1, which kind of looks like an exponent, but it's not a typical exponent. It just means sine inverse. So this is literally sine inverse, and then whatever you do on one side, you do on the other side. And then because these are inverses, they're opposite operations, they're inverse operations, they cancel, leaving you with theta by itself. So we have theta equals sine inverse, or the inverse sine, of 0.2534. Then you can calculate this. We'll show you how to do part B, and then we'll calculate the numbers here. So we got cosine of theta equals 0.5. Leave ourselves some room here. And then we're going to do the inverse cosine on both sides. And these will cancel, leaving you with theta. And then we'll calculate that. And then finally, we have theta equals tan inverse of 1.3750 in the same manner. So in order to calculate this and input this into the calculator, you're going to need the inverse sine, inverse cosine, and inverse tan. So we're going to go ahead and show you that. So here you can find the sine. The inverse sine is this yellow. You can see this yellow inverse sine here, and this yellow cosine inverse and the yellow tan inverse. So if you see like that above the key, just hit the second key, and then you hit the function that you're interested in. Okay, so inverse sine, and then you type it in. So you got 0.2534. All right, and this is going to give you the answer in degrees. So we have 14.7. We're going to round it to the nearest whole degree, so we'll round it to 15 degrees. All right, and then we'll finish up cosine. So we have inverse cosine of 0.5341. So you hit second cosine. And we have about 58 degrees. And then finally, inverse tan of 1.3750. And we get about 54 degrees. All right, and that's how you work backwards to find the angle rather than the ratio. So example 5, find the measures of the indicated angles. So we have a triangle this time, and we're trying to find the missing angle. So what we're going to do is we want to note that we have the opposite side here. So this is opposite, and we have the hypotenuse, which is 4. And so therefore, by SOHCAHTOA, we have opposite over hypotenuse, which means that we want to use the sine. So the sine of theta equals opposite over hypotenuse. And then if we want to get the angle, then we're going to do what we did last time and take the inverse sine on both sides. So we got theta is approximately, and then we can find the angle by plugging it into the calculator. Before we do that, we'll go ahead and do B. So we have opposite over adjacent. So we have that's going to be a tangent, TOA. So we got tangent of theta equals opposite over adjacent, which is 2. Then we're going to do the inverse tan. So theta equals inverse tan of 3 over 2. And we'll calculate those numbers. So again, we're going to hit the second key, sine inverse, and then 1 divided by 4. This time we're going to do 1 divided by 4 because that's the same thing as the fraction there. And we'll get 14, or about 15. Well, we're going to round it to the nearest whole. So we're going to round it to 14 degrees. Then we'll do the inverse tan of 3 over 2. So we're going to hit the second key. Tan 3 divided by 2. Get 56 degrees. All right, that's going to do it for the video, guys. I hope you found this useful. I hope you took a few things. And as usual, I'll see you in the next one.